All right, it's time. Here's Brandt with his talk.
All right, so instead of giving this talk tomorrow, by the way, can everyone hear me? Or?
Yeah.
Okay, cool. So instead of giving this talk tomorrow, I'm giving it today. I'm going to be sharing a little bit about something I have been thinking quite a bit about for the last few months, which is what Python's future JIT compiler might look like, or CPython's future JIT compiler specifically. So I'm going to start with some background, and this kind of will also be good background for Ken's talk immediately after this on optimizations that we hope to perform. Specifically, I'm mostly going to be kind of talking about some experiments that I've done with actually generating and executing machine code, not necessarily optimizations and things that happen in the meantime. However, I will be giving some background on that because I think it's really helpful for understanding how everything ties together. So, a little recent history. In CPython 3.11, one of the headline features was the specializing adaptive interpreter. And so this delivered really good speedups. I think the number we quoted most widely was something like 25%. If you want to take that at face value, that it was just a one-time performance gain that was nice to have, then sure. But if you think about it and you read a little bit between the lines, you understand that we're now collecting runtime profiling data for user code. And that's something that we can use later if we want to lower that code and make it more statically typed. In CPython 3.12, we got a nice quality of life improvement as maintainers. We started generating the interpreter cases, the main switch, from a domain-specific language. And this allowed us to analyze and modify parts of the interpreter at build time. This is really helpful for the people actually working on the bytecode because we can worry less about things like error handling, reference counts, adding counters and stats and all those sorts of things. But at the same time, again, if you can kind of read between the lines, we now are able to generate multiple interpreters from a single source of truth. And we also are able to generate lots of metadata by analyzing that single source of truth. So in 3.13, and again, this is all stuff that's actually currently on main, we do have an internal pipeline for detecting, optimizing, and executing hot code paths. So this is off by default, but if you build Python and you set the right environment variable or pass the right X option, it's called UOPS, U-O-P-S. Basically, CPython will find hot loops in your code. It will basically build a trace of that loop, and it will break it up into a more efficient representation and optimize it, do some light optimization, and execute it in a second interpreter. Now, currently, this is actually a little bit slower, so you don't want to turn it on. It's like 5 or 6% slower just because it's kind of the first phase of this entire pipeline. And in the end, the interpreter isn't really what we want to be executing these things in. I'll get to that later. But basically, this wouldn't be possible without either of the first two steps. Being able to break big, complicated bytecode instructions down into more simple atomic steps is only possible because of the changes made in 3.11 for specialization, and in 3.12, where we're able to define bytecode instructions in terms of smaller steps. So I like providing examples just so we can kind of walk through what this pipeline looks like in practice and what it may look like in the future. So we're going to look at my Fibonacci function here. It's pretty straightforward, and specifically we're going to focus on the inner loop. It's pretty simple. We're just looping over the range, and then we update the values for A and B by adding A and B together. So if you look at the bytecode for this function, it'll look something like this. If you want to know how the bytecode works, you can look at the dist documentation, but basically these are generic instructions that have mostly remained unchanged since the earliest versions of Python. However, in 3.11, we got our specialized bytecode. So that took generic operations like for iter and binary op and allowed us to specialize those at runtime, for example, for iterating over a range object or adding two integers together. So that's great. Now in 3.13, we're building micro-op traces. And so these micro-ops are those smaller, more atomic steps that I was talking about that we're able to break individual instructions up into. So as I mentioned before, you can actually run these things off of main by passing the X option, uops. And when you do that, we will collect a trace for this loop, and we'll actually break each of these instructions up into their individual components. So you can see that for some of the simpler instructions, they may only expand to 2 micro-ops, and that's what we call them, micro-ops. But the more complicated ones, like 4-iter range or the integer addition, may have several different parts. And what's nice about breaking those parts up is that if any of the parts are redundant, for example, if we're checking that something's an integer when we can actually prove that it's an integer, then we can remove it. Or if we want to move things around, that's an option as well. So another thing that 3.13 main will currently do for you is we'll do some light optimization on these micro-ops. So currently the only optimization we perform is we'll find redundant frame pointer updates. Basically, if we have an operation that cannot fail or the control flow cannot move to any other point in the program, there's no reason for us to update the frame and say, oh, we're currently executing this instruction. So it's a very, very simple optimization, but it does work as a nice proof of concept. And so we will actually identify these 4 set IP instructions and just remove them for you. So that's just pure overhead that we're able to remove. In the future, and Ken will talk a little bit more about this, we'll be able to do stronger optimizations where we're able to remove more expensive checks. So for instance, if we can statically prove, as we can in the case of this function, that, for example, we're always iterating over a range object once we've entered this loop, and that A and B are both integers once we've entered this loop, then we can also remove those as well. And what's left is basically the bare minimum amount of work required to actually execute this hot inner loop. And you'll notice that this is entirely statically typed, which is great for further lowering. So once we've removed all of that kind of extra stuff that we can prove we don't actually need, then comes just-in-time compilation. And that's kind of what I'm going to spend the rest of this time talking about. We have a couple different goals with the just-in-time compilation. So our main overarching goal is to remove interpretive overhead. So we have removed all the extra sort of dynamic work that needs to take place. But there's still a lot of other kind of overhead that just comes from the way the virtual machine is laid out and the way it interacts with data. So we want to remove interpretive overhead by statically compiling these optimized traces. And statically compiling them allows us to reduce indirection through a few different ways. First of all, we can burn in, basically encode directly into the machine code the values of constants, caches, and arguments to instructions. So basically, instead of decoding an instruction's oparg every single time we execute that instruction, we can instead, for example, make it an immediate value to an instruction in actual machine code, which replaces a memory load, is a lot more compact, and a lot more efficient. We can also do things like moving data off of frames and into registers. So the micro-ops still execute on a Python frame, which means that intermediate values that live on the value stack are all still being written to memory and read from memory. So if we can lift all of that stuff out of memory and into actual hardware registers, that saves a lot of traffic to and from main memory, which is always a good thing. Finally, we can bring hot code paths in line. So instead of having a large interpreter where we have all of these different cases that all need to be present because we can jump into them at any time, here we can make a straight line code path that executes exactly those instructions that I showed on the previous slide. Now, these need to be weighed against some practical goals, right? I don't think anyone wants me to dump a 10,000 line C++ JIT on us, right? So the first thing is broad platform support. Python runs lots of places and our JIT should too. I think that this is an ambitious goal, but it's an important one. I think that it should have few runtime dependencies. For example, I would like for this JIT to be in a place where, for example, users wouldn't need to have a full LLVM install, for example. I don't think that's a good user experience. It can maybe be made into a good user experience, but I think I'd rather start from a place where You just download Python the same way as you always have, and everything just works. And finally, and perhaps most importantly to me, low implementation complexity. CPython is overwhelmingly maintained by volunteers, and so I think that being able to keep the complexity down is a really, really important goal to keep in mind. In fact, I personally feel like it's worth sacrificing peak performance in order to keep the implementation as simple, easy to maintain, and easy to understand and teach and learn as possible. And so these are competing goals, right? Like, we want to make things fast. We're also willing to, as I said, sacrifice peak performance to make sure that, this is something that we can all understand and that we can all maintain for the long haul. So, one kind of recent development in JIT compiler technology is something called copy and patch compilation, and it actually fulfills many of these goals in a really satisfying way. So if you haven't heard about it, which I hadn't heard about it that long ago, copy and patch compilation comes out of a Stanford paper, but if you don't like reading the paper, I highly recommend the blog post. There's a blog post called Building a Baseline JIT for Lua Automatically. This is by the same author as the paper, and I've actually spoken with him on a couple occasions. Basically, this is a way of turning a C interpreter into a fast template JIT compiler. And what's really, really nice is that we are able to maintain that single source of truth for how a bytecode instruction should be implemented. And it doesn't require us to handwrite assembly, which means that if you want to fix a bug in the interpreter and you already know how to fix bugs in the interpreter, the JIT will be fixed too without you having to actually do anything. We have that one source of truth and everything's built automatically for you, but the JIT itself is still really fast and has good quality code. If you don't believe me, here are some numbers from the paper. Compared to a WebAssembly baseline compiler, copy and patch has 5 times faster code generation and 50% faster code overall. The code quality is really good, and I'll show you why in a second. Compared to a mid-tier compiler, like a traditional JIT tool chain, which would be LLVM with a low optimization level to keep things fast, it has 100 times faster code generation and still 15% faster code. And just to kind of complete the numbers, compared to a full optimizing JIT with handwritten assembly, so in this case Lua JIT, a copy and patch Lua implementation, it's still faster on some benchmarks, and it's only 35% slower overall, despite being much, much simpler to maintain. So, how does it work? Well, let's think about the kind of simplest form of a template JIT compiler. If we want to compile a sequence of bytecode instructions to machine code as fast as possible at runtime, what it might look like is walking over that sequence of bytecode instructions, and then for each one, copying over some static pre-compiled machine code into executable memory, and then going through that machine code and patching up instructions that need to have runtime data encoded in them. So these would be things like opargs, constants that we want to burn in, things like that. Now, if you look at these two requirements, you'll notice that this sounds a lot like something we already have, which are relocatable object files. So I could just as easily say, when linking or loading an ELF file, we want to copy some static pre-compiled machine code into executable memory, and then we want to patch up the instructions that need to have runtime data encoded in them. These are relocations for like extern symbols. And so this is how copy and patch works. Basically, we will use LLVM to build an ELF object file, and then we parse out the stuff that we care about from that ELF object file, namely the body of the bytecode instruction and any information on how we need to fix up the stuff that we want to fix up. So I'm going to give you a concrete example, and by concrete I mean I'm glossing over some details, so take everything at like 80% face value, okay? So we have a load fast instruction here. We are going to take the body of that load fast instruction, we're going to put it inside of some other code that is going to be sort of the scaffolding that we need to be able to extract the stuff that we care about later and be able to stitch everything together. So in this example, we are going to be burning in the oparg, and we are going to be basically jumping into the next bytecode instruction, because we need to make sure that the code is laid out in a way that we can flow from one instruction to the next, and that LLVM won't like move things around on us. So you see here I have sort of some placeholders here, some things that I don't define for magically inserting the op-arg and magically continuing execution. Copy and patch solves this problem by using externs. So instead of using the value of the extern for our op-arg, we use the address of the extern for our op-arg, which allows LLVM to generate really efficient code that we can patch very, very easily. When you're actually fixing up relocations, typically you're inserting the address of the extern into the relocatable code. And so with this, we don't actually need to dereference the value at that address. We can just use the address directly. And so the code is really efficient. And since we're using Clang, we have this beautiful must-tail attribute on the final continuation call, which means that we will just get a single jump that we can use to flow into the next opcode. And even better, if the next, if that jump happens to be a length 0, we can just skip the jump entirely. So the object file that we get out of this when we compile this to ELF looks a lot like this, and we have everything we care about. We have the machine code here, highlighted in blue, and we have the relocations and where their data is going to go. We know exactly how the data is going to be patched, and we know exactly where it's going to be. And so we can take this, parse it out, and put it in static header files. And now we have all the data that we want to copy, and then all the holes that we want to patch. I've been working on this for a couple months, and I've done this. So if you want to check it out, it's on my fork of CPython. The branch name is Justin, as in just in time. So if you want to check it out, it works. You can also just actually look at the code by going to GitHub and checking out my branch there. Just some kind of stats on the implementation itself. At build time, it is about 700 lines of complex Python. So this is Python code that handles actually extracting all the cases, compiling each one, parsing out the ELF, and then generating the header files. It has about 100 lines of complex C. Those are the templates that I showed you that we actually insert the cases into so that we can compile and extract them. And there is an LLVM dependency. But most importantly, this is a build time dependency, not something that users need to install. Compare this to the runtime requirements. So we have 300 lines of simple C. Again, the nice thing about the copy and patch compiler is that it's really fast, but it's also really simple. It's a mem copy, and then walking over the relocations and just performing them. And then we have the 3,000 lines of simple generated C. And it truly is just as simple as the code that I showed you on the last slide. And most importantly, no runtime dependencies. Everything is fully self-contained. And what I really like about this is that from a maintainer point of view, I like that all the complexity has been shifted to build time rather than runtime, and it's been shifted into Python code rather than C code. So we are able to do all of the kind of fancy stuff later when we actually start making this thing really, really fast and really, really performant and optimizing the code in the Python code itself, rather than doing most of that work at runtime and in C code. I think we can all agree that we prefer writing Python to C. Yeah, Pablo, did you have a question?
Yeah, so I'm curious why you need LLVM as a dependency. Like, if I understand correctly, when you want it to generate the object file,
the ELF, yeah.
The text segment of that, put it into, like, parse it and put it into these templates. But couldn't you just use whatever compiler you're using to compile Python to just compile maybe these templates and just parse the result below?
Yeah, so there are a couple reasons. So the first one is that must-tail attribute where we get guaranteed tail calls. Yeah. GCC doesn't have that, and we need tail calls for correctness, otherwise we'll blow the stack.
You need Visual Studio to do it, like every compiler would need to support this in 100.
Exactly. Clang is a great cross-compiler, so it works lots of places. And we also use some other LLVM tools. For example, we don't actually parse the ELF. LLVM has a tool that will dump ELF to JSON, which is great. So we actually just parse the JSON, which is beautiful. It also has a built-in disassembler. So the 3,000 lines of header file is actually annotated where above each kind of dump of the assembly, we actually have the human-readable assembly output as well that you can audit and look at. And another thing too is once we start getting really clever with this, there are actually really cool things that you can do by using LLVM's wide variety of calling conventions. So for example, they have calling conventions that pass all arguments in registers and have no callee saved registers, which is ideal if you want to like pin stack items in registers and make the jump at the very end of the continuation really, really clean. Yes?
Separate question. The build time dependency, is that build time or is it generate files time? Could we separate that out?
We
For
could.
instance, for Python releases.
Yeah. Yeah, the only thing we're using LLVM for is to generate one header file. So currently on my branch, that's not checked into the repo because it's platform specific, and even whatever your PyConfig looks like, it can change the way it works.
Okay, so it does need to be built.
Yeah, we could choose to check those in or host those somewhere or whatever.
Well, if it's configure specific,
Yeah,
then you can't check them in.
And platform.
yeah, yeah. I choose not to track it. You know, yeah. So it is technically generate files time, but it's not checked in, so it's build time effectively.
Well, it also, I mean, all the other generated files we have
Yes.
are platform agnostic.
Yes. Yeah, yeah. I understand the question now. Yes, it's build time.
Okay.
Yeah.
Can you put it in a container, like the thing that we're using for configure, so everyone can run the commands and get the same outputs?
No, because it depends on the platform. So you would need a container for your specific platform.
It would be for every platform, every option of whether you have asserts turned on or off, debug turned on or off.
Yeah.
By the way, you can put asserts and printfs and stuff inside of your cases, and they'll just be in the assembly. It's awesome.
How long does it take a build time again?
It depends. You have one of the new Macs because it takes like 30 seconds. On slower machines, it's less than a minute. And it doesn't always rerun. So for example, I have it cached so that it won't regenerate if the file's already present and the generated cases haven't changed.
Yep.
So in practice, if you're not modifying the interpreter, you won't see it, but otherwise it takes a few seconds on fast hardware and no more than a minute on everything else.
So how does it work on Windows?
Oh, let's talk about platform support.
All right, yay for the plan from the audience.
Victor, you will be happy to know that the initial implementation supports two platforms. It supports 32-bit Windows and 64-bit Windows.
Microsoft.
Just kidding. It supports all Tier 1 platforms. If you check it out right now on any of these, it'll work. In fact, it supports all Tier 1 and Tier 2 platforms right now. Except PowerPC, but we don't talk about that. But most notably, since Clang is such a great cross-compiler, the default cross-compile setup just works perfectly. If you're doing cross-compiles now, don't change anything, just install LVM 16 nearby, and your regular build, your cross build, whatever options you're passing to configure, things just work. And I think that's it. So no questions, thank you. Sorry, Victor? Did you have a question? Okay, yeah.
No, I was going to say, how does it compare to Numba, and does it work with GPUs?
How does it compare in terms of speed?
Yeah.
So currently it is no faster than main when you have this turned on, but that represents a 5% improvement over the micro ops that it's based on, and we haven't done any of the fun tricks yet.
Okay.
So it's much slower than Numba. And what was the other question? Numba?
GPU support.
GPU support, I would guess just as well as LLVM supports GPU. So I'm not doing anything special. Yeah.
Because they aren't CPUs and the resources aren't in the right place, so it's weird.
Yeah, it's nice because for things like platform support or more specific like hardware integration, we can just piggyback on LLVM. So if there's a way to make LLVM use the GPUs more effectively, then we can harness that too, at least for that build.
Yeah. Okay.
Yeah.
So
Victor.
the thing about container, is it possible on Linux to generate the generated files for all platforms from Linux?
Yes, so if you
compiler container with 20 cross compilers in it, I think.
you don't need the container. So if you install the cross compiler toolchain, LLVM knows how to find that, and you can just build them all. Because you don't actually need to run anything for this.
He really wants to use a container.
He does.
It's just that when you ask people to install LLVM, they get different flavors, different flags, and the output can change. So
Yeah,
we need to
Yeah, that is definitely something important, but again, remember, this also depends on configure flag, so it's only as stable as those. Also, on top of that, I mean, I do have CI running this on all the platforms I listed there. And it's also tested against the full matrix of LLVM 14, 15, and 16. So for all three of those, I've verified that this passes the entire test suite.
So are you going to checking this file in Python?
I have no plans to.
Okay.
We should.
You should not.
You can host a bunch of them somewhere if you want.
It's like, I'm not sure we're gonna need to configure. Basically, it sounds like this is working on a wide variety of things. It's just a matter of.
Yeah, and if you check out.
Is installing LLVM a problem for people who are building Python? And
Yeah.
the people in this room is probably not, but.
And if you check out my branch too, there's a README in tools JIT. It tells you how to install LLVM on all platforms. And again, one thing I want to highlight is you don't need to build CPython itself with LLVM or even the same version of LLVM. LLVM is only used just for generating that one header file.
So far, when you get a tarball of Python, you don't need LLVM, so it would be a new dependency.
Yes.
If you want to build the JIT, yes. So I imagine this behind a configure flag, where, I mean, just spitballing here. If you don't pass the configure flag and you don't have LLVM installed, we just do a normal build. If we smell that LLVM is nearby, but you didn't pass the flag, we can say, hey, by the way, you can build a JIT if you want to. And if you do pass the flag, then we build the JIT.
You can also leave work for future of, seeing if you can make something work on other compiler versions of this or not. It becomes a section of work for each compiler.
Just flagging that making that configure flag an optional thing is pretty much essential for iOS because you can't do it.
Or like WebAssembly, for example, or any of the list of tier 3 platforms that we absolutely can't build for. Yeah. Pablo, sorry, I shouldn't say names.
Do you need any special magic thingies for macOS? Like I recall that they have some protections against random executable memory.
This is, I mean, JITs work on macOS, so you can't have writable executable memory, and I think as of Sonoma you can't have readable executable memory.
Right.
Which is something I need to fix. So this won't work on Sonoma because currently the memory is read execute, but that's on my list of things to fix.
But do we need to is this going to change the way we need to release this for macOS? I recall that there's a way to ask for it, to say my binary.
When you map the memory, you ask for the JIT. In the flags, when you map the memory, you can say mmap JIT, I think.
Yeah.
And that says I'm a JIT.
I think you may be referring to platform restrictions where you need to actually set the executable up specially before you even run it.
Let me refrain. So when we build the macOS binaries or we distribute, because I suppose for the one that you compile is the same as when you compile yourself, right?
Yes.
Do we need to do you know if we need to set anything or ask Apple for?
If we do, I don't know that we need to. I'm not familiar with how we're actually building macOS releases differently from how I just build it locally.
Right.
I can vouch for it working locally.
Yeah.
Presumably, the release manager needs to use that flag.
Yes, if there's anything that needs to be done, that sounds like the release manager should do it, but I'm not aware of. It very well could be. Most of the sort of permissions stuff I've had to debug has been on macOS, specifically M1 Mac. Yeah.
So it sounds like the runtime code generation is super fast.
Yes.
Why not just do this either for the tier 1 or tier 2, I forget what number it starts at, interpreter.
Yeah.
Why only do this for tier 2?
Well, we definitely don't want to do it for unspecialized bytecode, right? Because the specialized bytecode is where we're able to actually generate high quality code for. And the reason that we want to break it up into tier 2 code is because just by breaking it up, we're not actually gaining anything, right? If anything, we're losing something because LLVM is able to optimize less over the same context. But the kind of reason to build this on top of tier 2 is because ideally we're going to optimize tier 2, and Kenjin will talk a little bit more about that. But if we're able to remove guards or reorder things or hoist guards or whatever, then this builds on top of that. And so those guards won't be present in the generated machine code.
I get all that, but like, so the examples you're talking about that are already using this, are using this for their baseline, right? They're using this
Yes.
before any optimizations.
Yes.
So wouldn't this be advantageous in the same use case for Python?
It could be. I haven't tried it.
Very much. We currently can't translate every tier 1 bytecode in the corresponding sequence of tier 2 bytecodes.
Although we have
Can
to.
you translate every tier 1 bytecode to copy and patch?
No, because the
No.
copy and patch input needs to be tier 2
Well,
bytecode, which is much simpler than the tier 1 bytecode.
We could. It would just be different. Yeah.
To explain this?
Sure. No, go ahead.
It's specialization. It's basically all around specialization. You want to do that dynamically, so you can't modify machine code. Well, you can, but it's a real pain.
Although we have.
And we want effective profiling that it gives us as well. So the tier 1 stuff, because we're eventually specializing very quickly and dynamically, we've got eventually profiling information as well. So we get effectively the free profiling stuff that we can set ourselves up for compiling. Because just generating tons of machine code is not very useful. It's not that we can't produce it quickly, but probably the code itself won't be quick on service.
It takes way more memory.
Another thing too, I realized I didn't mention. The reason that the generated code is such high quality is because we don't care about like the compile times when we're actually building this thing, so we pull out all the stops and tell LLVM to optimize heavily, which is something you wouldn't want to do in a real-time JIT. Yes?
When you generate the machine code, you said LLVM, can you pass the equivalent to compiler flag? Like, can
Yeah.
you say, like,
We're using Clang.
oh, it's client directly.
Yes.
Right.
Yeah, so we compile first using Clang, and that turns C code into LLVM textual IR.
Right.
The only reason we do that is because we want to fix up the calling convention, and Clang doesn't actually let us have this calling convention from C. So we fix up the calling convention using a hacky regex replacement that will change in the future. And then compile again to the ELF.
And you said it was under your org?
Yeah, so my user, Brandt Bucher, it's on my fork of CPython. The branch
Oh, it's
name.
on the fork of C.
Yes.
Show the URL again.
Yes. That's the URL. So it's the Justin branch of Brandt Bucher CPython.
That's what
And if you go to Tools JIT, there's a README in there that says how to install LLVM.
Sweet.
It's more a question of the general approach than what we did so far. But once you have a linear trace and you can have individual calls to this function, another obvious thing to try is to put all these calls into a C file, compile it all together, and see what happens.
Yeah.
Have you tried?
No, but one thing the paper did have good success with is actually compiling super instructions for common pairs or triples.
Oh, okay.
Because then it really allows LLVM to optimize across.
Yes.
Especially for example, like obvious things that we may want to look at are so the micro-ops are kind of expanded from a single instruction. I would imagine that in many cases, we aren't able to optimize that very heavily, and so it ends up being the equivalent of the original instruction. So that'd be sort of low-hanging fruit for things that we could compile. And again, when we're just walking over, we can window over and see if we have anything that's...
Yes, also a tire X.
Yeah.
It could be really involve the compiler and see what happens.
Exactly, and right now we have we have one template for every micro-op, so like 200 some odd templates. In the paper, they generated as many as like 10,000.
For combinations.
Yes, and not only for combinations, but also like, for example, if you have some instructions, for example, the control flow changes based on the value of the op arg. So it may make sense to actually burn in values of the op arg, not actually at JIT time, but ahead of time, where you hard code those values and LLVM can optimize based on them, and the op arg is completely removed. Then there's also super instructions, and there's all sorts of games you can play. Another example would be if you're lifting things from stack items into registers. If you are kind of keeping that mapping of stack items to registers, you may want to compile variants for different stack sizes so that you have a finite number of mappings, but you're able to keep things relatively simple. Victor again.
So what is your proposal? Do you want to merge your work, or do you want to maintain it outside Python for now?
I didn't really have a proposal today, but it basically, if this is something people would like to see in main off by default, we can get it in main very easily. I know we aren't crazy about experiments in main, which is kind of why I'm floating the idea now. If not, this has been a long-lived branch since like May, and so if it's any testament to like how easy it is to maintain this stuff, a lot of stuff has landed in main since May, and keeping this branch up to date and improving during that time has not been very difficult. Ken even borrowed, he basically merged this branch into his own branch a while back when he was playing around with the optimizing stuff and wanted to see what would happen if he JITted it. Ken, is it easy to like add new bytecodes and work with the JIT as a like an API?
This is a great question. Yes. Yeah, the good thing is that you just need to install LLVM and the script will automatically generate it for you. So you don't actually need to know how it works in the background.
Yeah.
Oh, and because like you said, at runtime patching it in is really simple, so we actually had to modify the patching because our patches were of different types than linear tracers. But even then, like the file is just a for loop, like you mentioned, a mem copy, so it's really simple to modify.
Yeah, the actual code that JITs and copies and patches, like of those 300 lines of fairly simple C, like the hot loop where we're actually just walking over stuff, selecting stencils and patching stuff is like maybe 20 lines of code. The rest is sort of like handling permissions on Windows and Mac and all that kind of fun.
And is it possible to maintain it outside Python? I mean, just technically? I don't know if it makes sense. Or is the implementation entangled with the implementation of Python itself?
I would say that since we are using the same micro-ops as tier 2, we're pretty tightly coupled to the implementation.
Maintain it outside? So
It could be. One thing that we would need, so when we actually compile the code, we basically in those header files, if you have a bytecode instruction that calls, for example, pynumber add, right? That's a symbol that you need to link against. And so the way we do that in the header file is we actually just put address of pynumber add as an addend for that relocation. That works for pynumber add, but if we were building this separately from CPython itself, there's a lot of internal APIs that would need to be exposed as public symbols in order for us to link them, and actually linking them at runtime would be a lot more complicated. We would first probably need to initialize all the stencils when the extension or whatever was first loaded by walking over and the stencils and actually resolving all of those symbols, finding them in the current process using DLSim or whatever the Windows equivalent is, walking over them and actually fixing up those add-ins. And then it would mostly be the same. But that sounds a lot more complicated than, and I don't think we want to stick all that stuff as public symbols. So it is doable in theory. I think the ergonomics make it like probably not the best option.
I'm just trying to understand the advantages and disadvantages of maintaining websites.
Yeah.
Because, for example, adding a dependency to LVM is not that straightforward for me.
Okay. Then don't build the JIT. Or I'll build it for you and I'll host it in a container.
I expect that people will want the JITs.
That's why that's behind the configure flag for now. Like the answer to that is unknown. If this proves very useful, then we find a way forward to actually do it.
You can't at the same time say that you want the JIT and say that you cannot have this dependency, right?
This is what I want.
Yeah, I want $1 million. We all want things. I get it.
Finish the JIT and see what happens.
Yuri, did you have your hand up?
Yeah. So as far as I understand, there's pretty much no alternative to this. Like, if you want to go with the JIT, it's either us spending a lot of resources, handwriting all of this, kind of code paths, generating them, which is one of the hardest parts of the JIT. Like, this is a nice hack that allows us to spend a lot of resources and just reuse the code. So it seems like the plan should be to merge this to the main bridge as soon as possible so that these guys can just continue working on it. Like really, am I missing something? Is there like an alternative?
No, that's how I feel as well.
Yeah.
And another thing too, just since you mentioned handwriting assembly, is that the two are not mutually exclusive. So for example, if we see that there's a really common opcode, and we see that we can actually write it better than LLVM can for whatever reason, we can do that. The two play very nicely together. So it'd just be in that build script, the 700 lines of Python or whatever, we just special case that opcode and say, hey, use this assembly file instead. Yeah.
A quick question, follow-up question on the benchmark numbers that you showed in one of the slides. So basically what they did, they just replaced, so for example, in the case of Lua JIT compiler, they just replaced the handwritten code path, the handwritten assembly and whatnot, where the stuff that is generated with this approach from the slow interpreter.
No, it was a completely like new implementation that they wrote. So if you go to the blog post that I linked to earlier, it's a nice long blog post. If you don't know anything about JITs, you'll know how JITs work after reading it. And it goes over copy and patch and also things like inline caching and whatever, but it's basically him implementing a Lua JIT,
okay.
Right? And so it's the...
So then it's super fast.
Yeah, so it's the comparison of his just from scratch implementation versus an established fast implementation.
What blog post is that?
I can put it back up there.
You could probably find it just by Googling for copy.
Yeah, if you search for, oh wait, did I skip it already? Hang on.
I never saw the link to the blog post.
It was underneath the paper. It's right here.
If you haven't linked those from your repo, you should check that into your
Yes, I should.
tool/JIT.
Indeed. So the top one is the paper. The bottom one is the blog post.
And I just posted, they did a presentation a few months ago as well.
Was that for the paper?
Really good slides.
Yeah.
And just as an FYI, well, like that may be a new paper, but we were doing this type of approach for a translator at Transmeta 20 years ago, and I doubt we were the first people doing this, but templates from regular C code were very fast to JIT.
Yeah, how was your experience with it?
I mean, we shipped it in the product.
Okay, let's ship it in a product.
It was our intermediate JIT. It was the quick to produce code one, and then there's the optimized one later.
Yeah, I mean, it is, I kind of view this as like a baseline, but a really good one.
Yeah.
Right? And so if we wanted to have another tier where we pull out all the stops on top of this, that's a bridge we could cross, right?
Yeah. This is easy to maintain, like you don't have to modify assembly, you modify the C code. Like that was key.
Another question in terms of the code style, will you need to change a lot? Like, I know that you compiled some of the functions already in the prototype, but will the code style change? Or it's essentially the same thing, maybe with a couple of macro elements that you just need to copy?
When you say the code style, so we extract, so basically...
The way you write code, essentially, for all
Python code?
All code, yes.
Well,
Okay.
I'm sure you'll see lots of blog posts of how to get the most out of CPython's new JIT, you know.
But those are all written by, you know,
background.
So.
Yeah, no, I don't think it'll be any different than the specializing interpreter, where it's just we play to the benchmarks we take to be somewhat realistic, and we look to confirm that that is true in practice, right? And I'm sure that there are people who, you know, like try to optimize for the specializing interpreter, and I'm sure there'll be people who try to optimize for this, but I think in general it'll just be a good low overhead way of speeding up kind of the world. Pablo?
We already talked about this, but I want everyone to kind of discuss this. So what is the debugging situation of this code? Like, for instance, one of the things I mentioned is that I was a bit worried that since the JIT doesn't by default support have any sort of way to tell the debugger that, hey, this is the way you unwind through me. I assume that if you crash and use GDB or any other alignment, you cannot go through the code, right?
Yeah, so I don't know enough about unwind tables and that, and like dwarf and all of that to give a good answer. I can tell you that I don't include any unwind tables or dwarf in the JITted code, and we disable frame pointers. But if it's something that can be reused from the original ELF, then that's something that would be easy to harvest. Otherwise, we would have to kind of emit it ourselves.
Like one cheap way would be maybe at the beginning when, at the beginning maybe when we are playing with it, maybe a cheap way is to allow at least or detect if you're building Python itself with frame pointers and then generating the templates with frame pointers.
Yeah.
I assume you're going to copy whatever ends being there, right?
Yeah, so we're disabling frame pointers right now just because we're passing arguments in registers, and that's a valuable register. But I mean, this argument's been had a million times, so we can build with frame pointers. It's easy enough just to say don't use that register, right?
Right.
And so that could be the first step, and then again, I would need to do more research if I were to do it myself.
Well, at least having a sketch patch, I think, as a first kind of line, especially if it's cheap and for frame pointers, I think it's already useful.
Yeah.
In case, like someone wants to keep the needle more on the right side. But obviously at this stage it's too early to even.
Yeah, if we were if we could just extract all of this stuff from the ELF file, is that something that could be reused or would need to be different every time we emit a copy of that stencil?
You will probably need to patch the relocations as well.
So there's relocations in the
Not per se,
unwind tables and stuff?
The dwarf tree has what is called add ranges, and those will change when you place the code in different places. So you need to somehow say, oh, this code now lives here, so you need to say, oh, now I need an address, and you can update the thing. But most of the annoying stuff to generate, you can just copy paste.
Okay, yeah, if it's anything like the mechanics of extracting, like, for example, static data, BSS data, executable text, and if processing relocations on those, then the mechanics are almost identical, it sounds like.
It depends on how annoying it makes it to retrieve it from the file, but if it's very easy and you can have some JSON output, I suppose it's, but it's not like something that I think is super important at this stage.
Yeah, the two flags that I passed to Clang currently are omit frame pointer and no asynchronous unwind tables.
Right.
So if that's the sort of stuff that just gets dumped in the ELF file and is reusable, then it sounds like we have a promising path forward for a good debugging experience.
And like other JITs like Java has dealt with a lot of this stuff in the past, so there's a lot of things we can lean on for how they got debugging to work with their stuff.
Oh, I did see.
And I think we're getting too much into implementations details.
I'll be here all week.
So yeah. Thanks, Brandt.